last time we started talking about calculus, and in particular, we talked about how the pure math ideas that you develop in a calculus course can be connected to various real world contexts, not only to apply the ideas to those contexts, but actually in the other direction as well, to appreciate the calculus ideas better by giving the components some interpretation. So here's an example. This is sort of a slight modification of what we did last time. So suppose that you earn an additional 80 cents for each minute that you work. And suppose further that your marginal tax rate is 25%. Then the net pay on the next minute of work is going to be 80 cents minus that 25% of 80 cents. So in other words, 60 cents. All right, so that's fine. Question though is, what does this have to do with the chain rule? How can you apply a chain rule interpretation to this setup? Yeah, so we're looking at a composition. So I have a few answers here. So yeah, we're looking at a composition of two functions. So we have one function, which is going to take us from the gross pay to take-home pay, and another function that takes us from the minutes worked to cents earned. So what we need to do to realize the amount of change induced by the change in the amount of time worked, so one additional minute worked, is just multiply those two derivatives. So the chain rule says that the derivative of f times the derivative of g is equal to the derivative of the composition of f and g, and each of those functions just needs to be evaluated at the appropriate point. So the current value of whatever the input to that function is. So g prime is evaluated at the current number of minutes that you've worked, and f prime is evaluated at your current pay. And you get 60. So 0.75 times 80 gives you 60. So the point of this little exercise is not to solve that question, because the question is pretty simple. You know, we really just multiplied two numbers, and we also didn't really use any, or didn't need to use any advanced math ideas, not even calculus, to appreciate this. So you can imagine you could give this problem to a middle school student before they've seen any upper level math, and they would still be able to say, all right, well, I see that 80 cents, I'm going to subtract 25 cents from it, or sorry, 25% from it, and I'm going to get 60 cents. Right? So the problem is not that complicated, and bringing calculus into the picture doesn't help solve that problem. It's already simple enough and complete as it is. The point, rather, is to go the other direction. So you want to understand the chain rule through the context of a simple real-world example like this, so you can appreciate how it's really not that complicated. It's just two multiplications telling you what happens when you scale once and then scale again. So from the data gymnasia, here's another way to think about the chain rule. So we have this visualization here. This, by the way, is from a 3 Blue 1 Brown video. So this is the way he does it when he talks about the chain rule. And this is just an interactive version of the same thing. So what we can see is that we can move the input however we want, and then also at the same time see what the function is doing to a nearby input. So we have t and t plus delta t, those are our inputs to the function. And you can see that things are getting stretched, like the length of this line segment and the length of this line segment are related by a certain ratio. It's getting bigger. And specifically that ratio in this picture is 1.644. So we're saying this has to grow by 64% to get us from this length to this length. And then same idea here, that it approximately doubles going from here to here. So if you are going to multiply by 1.64 and then multiply by 2, that's equivalent, if you want to do the whole thing in one go, to just multiplying by the product of those two. So this is a good way of kind of visualizing in one plane how the chain rule works. So this is another instance, I would say, where understanding the derivative in terms of a scale factor for converting small changes is much clearer than slope, because if you use a slope visualization to think about the chain rule, then the output of the first function is being visualized on the y-axis for a graph of that function, but it's an input for the outer function. So then it has to be on the x-axis for that. So that gets confusing. This is much simpler. You just have one single axis for each input, and the output is just shown on the next axis. So you can appreciate how when you change the delta t, the ratio doesn't change that much. And like down here, it's about 1.43 Yeah, I mean, okay, I guess it still changes pretty significantly on this particular scale. But in any case, if you make this really tiny, these ratios are going to stabilize. In fact, there's a homework question on this. I'll release the homework right after class, and there's a little bit better visualization for this. You can also see things in this visualization like what happens when the derivative is negative. So that's going to reverse the order of input and output. And you can see that here with these lines kind of crossing as you map from the top one to the second one. So anyway, I just kind of wanted to put this in front of you and give you a chance to play with it. And it's in the data gymnasia course as well, so you can look at it there, and there's a question you can work on. I want to go a slightly different direction though. I want to point at why we're using the chain rule here, why the chain rule is important. The chain rule shows up in a really prominent way in deep learning, which is one of the most sort of cutting edge, hottest areas of data science. We have a whole course dedicated to deep learning in the program. And the reason is that there's a lot of stuff you can do with it. There's a sort of big surface area of applications for deep learning. And a lot of them are really cool and can't really be done any other way currently. So it's a big deal. And the chain rule shows up a lot there for reasons that we're going to see. And I want to kind of preview that without getting into any actual deep learning in a way that we can kind of refer back to when we arrive at this later. So this is a little bit of a fuzzy question for now, and that's on purpose. So what happens, do you think, if we have 100 functions, which are defined in some way that makes them random? And the derivatives that you get when you look at just the derivative of one of those functions at some point of interest, it tends to be, let's say, fairly evenly distributed in the range from -3 to 3. So what do you think is going to happen if we look at the derivative of a composition of these 100 functions? It's maybe a little bit hard to predict for this particular setup what's going to happen. So let's actually compute and see the way it works out. I want to say here that the intuition is that it should be large, because you're going to get a lot of numbers that are, you know, as big as like 3 or 2 in absolute value. Some of the numbers will be less than 1, but most of them will be bigger than 1. And so you would think that it would kind of work out so that you have more numbers bigger than 1 multiplying. And if you have a lot of numbers, like imagine all 100 of these numbers are 2, then you're going to have an enormous number, 2 to the 100. So I would think likely large would be the intuition here. But then again, you might end up with a really tiny number in there somewhere, and that might sort of wipe out all of the contributions from the numbers that are bigger than 1. So anyway, let's actually see what happens. So we can do this with some code here. So we're going to import random sample from the numpy.random module. So that's just going to allow us to generate an array of random numbers between 0 and 1, uniformly distributed between 0 and 1. And we're going to import the product function, which will allow us to multiply all the values in an array. And then right here, this is a little bit of a hack. And I sort of wish there was a better interface here, because I don't think this is really the right way to do it. But if you multiply numbers between 0 and 1 by 6, now you've got numbers that are between 0 and 6, and they'll be uniformly distributed in that range. And then you subtract 3 from each of them, and that's going to shift that whole window over, and you're going to have numbers between -3 and 3. So this is how in NumPy you generate some numbers between -3 and 3. And the reason I don't love it is I think like making the user do this arithmetic of 3 minus -3 equals 6 and then type that number here, I don't think that's totally great. But anyway, it is what it is. And we can multiply this out. And interestingly, in this case, we did get a small number here at 0.02. And I guess what happened is one of these numbers happened to be super small, and it kind of wiped out all the contributions from the numbers bigger than 1. But it happens that it's quite large, and fairly often it's huge. Like, look at this number. It's completely enormous. Anyway, you can see that we're all over the place here. We have some modest size numbers, some huge numbers, and occasionally have a really small number. So you can just run this a bunch of times to kind of get a feel for what's going on. You know, the take home here is that some kind of crazy stuff can happen when you're multiplying a whole bunch of numbers together, and those numbers are not controlled to be sort of pretty close to 1. If they even drift up to like 2 or 3 or down to really small numbers, then that repeated multiplication that you get from the chain rule, which says that compositions become products when you take a derivative, that's going to lead to some kind of weird numerical stuff where your derivatives are really huge or really small, depending on exactly how things shake out. And they can kind of end up all over the place. Oh, there's a question here. Right. So a couple of comments here. Why are we only thinking about absolute values? That's because that's the way multiplication works. So when you multiply 100 numbers, the sign is just going to be whether you have an odd number of negatives in that list. And so that really isn't going to affect whether your number is huge or small. But then you multiply all the absolute values of the numbers together. That gives you the absolute value of the product. And that's going to be really big if, you have, it sort of shakes out where you have enough numbers bigger than 1 and not too many numbers super close to 0. And so that's what we're thinking about here. So we're just sort of wondering, like, do we end up with really huge numbers or really small numbers or somewhere in between? And for that, just by the way products are defined, where you can split out the signs and the absolute values of the numbers you're multiplying, we can just focus on the magnitudes of the numbers. Yeah, so Nick also made a comment or a question here, and I'll let him expand on that. Yeah, that's right. So I think that the example might have been simpler if I had done, like, let's say 3 times random sample minus 1. So this is going to be, sorry. See, this is what I mean. You have to do this map in your head, and you shouldn't have to. You should just be able to say, here's the range. Here's where to start. Here's where to end. Okay, 2 times random sample plus 1. So this is uniformly distributed between 1 and 3, and you're not going to get any factors less than 1 that are going to bring you back down to Earth. Everything's going to cruise off into outer space. So if we do this, we're going to get totally huge numbers every time, 10 to the 29th, 10 to the 28th, etc. And even if we decrease it a little bit, like, between a half and, see, this is what I'm talking about. You have to do a bunch of arithmetic in my head that I don't want to do. So let's say it's between a half and 3. So most of them are between 1 and 3, but some of them are between a half and 1, but still those factors are not going to keep up. The factors less than 1 are not going to keep up with the factors bigger than 1. So we're still going to end up with really large values, not as large as before, but still really big. But then where the instability comes in is if you're between 0 and 3, and so you occasionally have a factor that's super close to 0, and that's going to bring the whole thing down. You're not going to get enough contribution on the upper end. We have to do it a bunch of times, though. It's interesting. This seems to be taking longer. Okay, here we go. We get 10 to the minus 6 here, roughly, approximately e times 10 to the minus 6. And the reason that happened is that there was just some colossally small number that happened to show up in this random sample of 100 numbers between 0 and 1, and that ended up counteracting the effect of all the other ones. So anyway, yeah, that's a good comment, Nick. All right, cool. And this is great, by the way. If you send comments in or questions as we go, then that gives me more ability to deviate in helpful ways from the script that I prepared, and I'm happy to do that. So feel free to continue to contribute questions and comments as we go. I would say there's been less of that in this summer session than there was in the school year when we were conducting courses through the same platform. So you should feel like there's some headroom there. Okay, I want to try a sketch question. I haven't done one of these in a long time. It's actually some old technology, but we'll see how it goes. So we want to sketch the derivative of the function whose graph looks like this. So we can snapshot this function, or sorry, yeah, snapshot this graph, and then you can delete that here and pop open your drawing tool. And now you can click the pencil here and you can draw however you want. If you delete it, you can put the background image back with this button in this lower left corner here. Yeah, so it seems like maybe people are having trouble pulling up the sketch tool. So I'll just walk through that again. I'll delete this. So yeah, you just want to snapshot the graph with the camera icon, and then you can delete this. You don't need it. And then pull up your drawing tool and it'll show up here. And then you can turn the drawing pen on by clicking the freehand tool. And maybe I'll switch to orange. And then we can draw here. If we want to select what we just drew and delete it, we can do that. Or we can delete everything and then replace the background image. Let's maybe do it together. So we just start over here at this extreme edge. And what we see is that the slope here is a little bit steeper than just like a line y equals x, like the northeast southwest diagonal. So the derivative is going to be bigger than 1 up here. So the graph is going to start somewhere up here. And then it needs to hit 0 by the time it gets to this local maximum. So it's going to somehow come down and hit 0 right there. And then it needs to hit 0 again over here. And in between, it starts out 0 and then it becomes negative and then sort of kind of comes back. So we'll do that. It starts out 0 and then becomes negative and then kind of comes back like that. And then same idea over this range and comes back to 0. And it gets quite a bit steeper. Notice this is pretty shallow and this is steeper than a slope of 1. So something like this. And it goes back to 0. And then same idea for the next little piece to the next local minimum. And then, so something like that. You can click insert and then send that. Yeah, I'm kind of realizing that having too much default teal can be not so great. Like here, it doesn't look great against that teal background. But anyway, it's something like this. So here's the actual derivative of the teal function shown in orange. So you can see it's sort of pretty similar to what we drew. Okay, so let's change gears a little bit. So it's kind of a few basic exercises with some calculus ideas. And here's one that's related to calculus, but we're kind of transitioning to where we left off last time. So we talked about how functions tend to be represented in applied math and in settings where we're doing things numerically. They tend to appear in formats that are different from how they show up in a calculus class. And this is an important thing to get used to and put a point on, in my opinion. So instead of having something like sine of 2x, we would typically use what kind of data structure to represent a real world function, like let's say the price of a stock over time. So yeah, it can be a list of X, Y pairs, or equivalently, you can visualize that same data structure in the form of a graph. But the important thing is that we're going to have sort of some samples. We'll know at 3 o'clock on Thursday, the price was 62.5. That data is going to have to go into the representation of the function. We're not going to be able to just come up with some elementary expression that gives us all of those answers at once. We just record those answers, and that is the representation. So the idea is going to be an ordered list of key value pairs. And the way that that data is actually represented in memory is not sort of one particular thing. There are lots of possibilities. So we could have a dictionary, which is a natural key value store, except that it really should be an ordered dictionary where the keys are kept in order because they are representing real numbers which have a natural order to them. We could use a pair of lists or arrays. I think in a lot of ways this is kind of the weakest way to do it because now you have 2 data structures instead of 1, and there has to be some understanding of how they correspond to one another in order to give them a meaningful interpretation. But that is also the default way of doing it in every standard plotting package. So it is an important one. We can use a table like a pandas data frame. I think in a lot of ways that's the most principled way to do it because it gives you a lot of the advantages of a dictionary, but it also presents in a table when you do it interactively in a Jupyter notebook, and it has other affordances that are appropriate to tabular data. But in any case, let's proceed with this pair of lists or pair of arrays concept and pick up where we left off last time. So the prompt is going to be, so you've seen this already right at the tail end last time, but let's do it again now. So the prompt is going to be to come up with a function that approximates the derivative of the function represented by these 2 arrays. So here are all the X values, here are the corresponding Y values, and we can plot that. Sorry, I forgot to import array from NumPy. So from NumPy, import array. So you'll have to add that. So lots of folks are still working on this, kind of giving folks time for it, but maybe we should proceed and work through it together. So yeah, there's some NumPy array operations here that folks aren't super familiar with. So let's walk through that. I'm trying to think of how I want to proceed here. So let's maybe make a scatter plot as well, so we can see the actual point. So here are the X points and the Y points that we get for the graph of this function. And all we can really do, because we have these sort of straight line segments, is we can sort of say, well, in this area, this general vicinity, the derivative is approximately whatever the slope of this line is. So if we want to represent the derivative, we really probably should just have one data point in this range. It'd be kind of false precision to have a bunch of data points in this range where we have just one line segment here on this graph. So maybe let's choose the midpoint of this particular interval, and we'll say, and then we'll also work out the slope. And so we'll say for the derivative, we'll have a single data point, which is at this midpoint in terms of X, and then the Y value is going to be the slope. So that's kind of the concept. But let's break that down. So I'm going to improvise a little bit here to kind of break this down for you. So how can you calculate the sequence of midpoints of the X values in NumPy? So let's just make that one sort of atomic question. So given an array X, how do you calculate the sequence of midpoints? So it should be a one-liner. I think I see one correct answer in the works here. I think it's understandable. It's the sort of thing that either you've worked with NumPy or some similar package before and you're used to these array operations, or you haven't and you kind of have to write everything out manually. Let's break this down. So I'll try to break out my whiteboard here. So suppose that that your X values are, I don't know, 1, 5, 9, 10, or something like that. And we want to compute the midpoints, which are going to be like 1 and 5 average to give 3, 5 and 9 average to give 7, 9 and 10 average to give 9.5. So one slick way to do this is just shift the array over. So we can do X bracket 1 colon, and that's going to be 5, 9, 10. So we slice it. I said shift, that's the wrong term. We should slice it so that we get the first term through the end. And then we can also slice it so that we get the first 3 terms, 1, 5, 9. And how do you slice an array to get all but the last term? We can do colon -1. So that slices from whenever you have something missing on either side of the colon in an indexing operation that's understood to be either start at the beginning if it's before the colon, or go to the end if it's not. So that's why you have 1 colon here and colon -1 here. So in any case, once we have these 2 arrays which have dropped a value, we can add them and we're going to get exactly twice what we want, 6, 14, and 19. And so then we just need to multiply that by 0.5. This stuff and move it over. Okay, so this is the idea. We want to do 0.5 times the sum of the 2 different ways to slice the array in such a way that either the first or last entry gets dropped. So we want to do 0.5 times X sliced from 1 to the end, and X sliced up to the last term, but not including it. So that's the solution. Okay, so I'll share what I actually had prepared now. So we'll use this operation to get the midpoints. Those are going to be the X's for our derivative function. So we'll have 1 fewer, which makes sense because, if there are n points here, there's n-1 line segments connecting the points. And then we just need to come up with the derivative. So maybe you've had some time to think about that. So let's ask that as its own question too. So how should we calculate the Y values? which we'll call maybe yd for the array of y values for the derivative. So we can use similar ideas, incidentally, to just kind of give you a hint. We can use similar ideas to what we did last time with the x's. Okay, so a few folks have submitted answers. Not many more folks seem to be currently working on it. So let's do it together. I might need my whiteboard again, because again, I'm improvising at the moment. So we want to calculate the slopes. So we're going to have a sequence of points and they're connected by line segments, and we want to calculate the slope of each line segment. So that means we need to compute the differences in the y's and divide by, and also compute the differences in the x's and then divide. So we can, so this is x1, x2, x3, y1, y2, y3. We want to compute the differences and then divide. So there are two ways to do that. One is that there's just a diff function in NumPy that allows you to compute differences in an array, differences between consecutive terms. We could just use that. Or if we didn't know that existed and we wanted to do it from scratch, we could compute the differences in the y's by the same idea. So we slice from the beginning up to everything except the last one. And then we also slice from 1 to the end, and then we subtract those two. This is the difference in y's, and then what we can do is just divide by the same thing to get the difference in x's. Same thing, but with x. And so this is going to be our derivatives. This is what we want. And we're actually going to make a plot here as well. So we'll compute the y values just like we just said. And actually, I did this sort of backwards, but it's backwards in the top and the bottom in the same way. So the -1 cancels. And then we'll just make a plot to kind of sit over the top of that original plot that we made. And that looks pretty good. This is a quadratic function. It's like x squared. So when you take the derivative, it's like a constant times x. So it should be approximately flat. And that's what we're getting here. So that checks out. This seems to have done a pretty nice job. And notice how it's staggered. You have these 2 points, and then this one is right in the middle, these 2 points, and then this one is right in the middle, and so on. So that looks pretty good. See if folks have any questions. Looks like no questions for now. So I want to go into a little bit of an aside. This is not calculus, but you might think it's more interesting. This little trick that we did for calculating the midpoints of an array, that is necessary because we have to keep everything vectorized to keep it performant in Python. So it would be more transparent, perhaps, to do something like an array comprehension, or rather a list comprehension in Python. So we could say for I in range from 0 up to the length of the array -1, what we want to do is average the x values that are next to each other. So xi and xi plus 1. So that's one of the values plus the one right next to it, divide by 2. And then create a list of those values and then make an array out of it. So that's sort of less of a trick. You look at that and you see, okay, you're averaging consecutive values. It looks like the math syntax for the corresponding operation, and the NumPy does not look like math syntax. Like you would never write something that looks remotely like this in a math class, right? That's a programming hack. But the thing is, you can't really do this. I mean, you can, but you shouldn't, because you're going from NumPy arrays back to Python lists and then converting back again into a NumPy array. And if you know that your arrays are always going to be small, you can just do whatever you want and everything's going to be fine because everything executes in, way less than a second. But if you have really big arrays where things are going to take a lot of time, or you need to perform the same operation many, many times, then you're going to have a problem because it's going to be really wasteful to be constantly converting back and forth between Python lists and NumPy arrays. We'll talk about that in Data 1050, what's really going on under the hood when you do that and why it's a problem. And so people teach you not to do that. They teach you to use vectorized versions of these calculations like this one. And the reason that this is called vectorized is that it's making the sort of actual operation happen in code that implements these operations for these arrays. So this slicing thing happens in the NumPy package. So does this slicing operation. And then when you add two NumPy arrays, Python asks NumPy like, hey, these are NumPy arrays. What do I do with this stuff? And NumPy has some code that implements this sum. And that code is what's being executed when you do this operation. Whereas up here, it's not happening in NumPy, it's happening in Python. Python implements its own list comprehensions. This has nothing to do with NumPy until we convert from the array here, and also this indexing operation. But this is definitely mixing Python and NumPy, and this is essentially just pure NumPy. And in a lot of cases, vectorization is a good idea no matter what, because it makes it clearer what you're doing. So this is sometimes, not all the time. I think this is an instance where it definitely does not make it clear what you're doing. Someone has to think through this operation in order to see, oh yeah, they're calculating midpoints. It doesn't just jump out at you. And that's an important distinction, something being sometimes a good idea and always being a good idea. Vectorization falls in that category. And you'll often encounter this mantra that like vectorization is where it's at. That's the key to efficient numeric computing, and that's what we need to teach everybody. Vectorization in every instance where you possibly can. And this is actually just not correct. This is a misconception. And the reason it's clear this is a misconception is that it's dependent on what programming language you're working in. So if you're using C++ or Rust or even Julia, there's no performance reason not to just write out a loop, sort of an equivalent of this expression in Python. It's going to be just as fast. There's no conversion back and forth between different things. It costs you a lot of performance and memory. You're just going to get the same performance regardless of whether you wrote the loop or whether you are able to call a library where some other programmer has written a loop that's getting called under the hood. So from this point of view, what we can say is that the central role of vectorization in scientific computing is really an artifact of the design of languages which happen to be popular, like Python or R or MATLAB, where library authors write code in a completely different way than ordinary language users. And so I think that's worth bearing in mind when you have some trouble with vectorizing things. You know, there's nothing wrong with you. It's just a sort of accident of history that's a really important thing to keep track of. On the other hand, this is the world we live in. Vectorization is important because these languages are really important. You can't avoid them. And it's important to learn how to use these little vectorization tricks wherever possible. And in situations where it's not possible, you want to learn what the workarounds are. So in Python, I would say the main two are packages called, well, a package called NumPy, and then I don't want to call Python a package because it's quite different from Python. But in any case, we'll talk about these ideas more in Data 1050. I just kind of wanted to preview that now and kind of help set some context for how you think about vectorized operations. And we're 30 seconds from 11, so I don't want to start something new. I'll just check in if folks have any questions. So I don't see any new questions, but feel free to send one in now if you have one about this business we just discussed or anything else from class today.